Around 1913, a couple guys, Lenore Michaelis and Maud Minton, came up with a theory of enzymes, and it just stuck. It has a few exceptions, but it works for the most part. Their theory was that you have an enzyme and a substrate, and that it's rapidly becoming this enzyme substrate complex where the enzyme and the substrate come together through hydrogen bonding, van der Waals forces, salt bridges, those type of things. They come together and combine to this enzyme substrate complex, and they rapidly also dissociate back to the enzyme and the substrate. Notice at this point that we haven't made any products. The enzyme hasn't turned this substrate into anything yet. That we've just had these two start off by themselves, come together, and then come back apart without doing anything. And so the reaction rate at which this happens, which the enzyme and substrate form a complex, is K1, and the rate which it dissociates is called K minus 1. Now this thing is in a rapid equilibrium, so we could say that there's a equilibrium constant. We'll call it capital K, and we want to say what's the constant of the substrate formation. So that would be the product, which is the enzyme and the substrate, divided by the reactant, which would be the enzyme substrate complex. So if we ask ourselves, at what rate does the substrate form, it would be equal to E times S over ES, which is equal to K, and that should be a lowercase k, so K minus 1 over K1. So note in this that, first of all, this is a capital K, so I'm talking about an equilibrium constant, and these are lowercase k, so we're talking about reactant rate constants. And the only thing I'm doing here is showing that this is an equilibrium, and so these are this equilibrium has a constant that's equal to the reverse reactant rate over the the enzyme substrate complex reactant rate. Now let's bring in our products. So if we say that we have E plus S yields ES, enzyme substrate complex, and we have K1 here and K minus 1 here, and then we have the formation of enzyme plus product, and we'll call this K2. So let's move this up here. So we're going to now make a couple of assumptions in our reaction. So our first assumption is that the this concentration of the enzyme substrate complex is constant. It's constant. And so that means that basically as this is forming into enzyme substrate complex, one of two things are happening. An enzyme substrate complex is either forming back into enzyme plus substrate, or it's becoming product. So this is happening, and this is happening. So K1 has got to be at least slightly faster than K minus 1, and much, much faster than K2. Now the second assumption that we have to make is that the velocity is measured, so velocity is measured, it's measured directly after adding the substrate in. So after substrate is added. And the reason we're assuming this is because an enzyme can accelerate it accelerates the substrate into product, but it also accelerates the backward reaction. And usually the backward reaction is going to be much slower because, especially if they're exergonic reactions, the free energy is much, much lower. But it does accelerate the backward reaction as well. And so since we're only focused on the formation of product, the initial velocity, we want to assume that we take this measurement of the velocity directly after the substrate is added. So we have basically zero product available, so no product can turn back into substrate. Now, of these assumptions, this one's the most important mathematically, so we're not going to make any mathematical measurements off of this assumption. We're just explaining something. So the first thing we can do is we can make a mathematical measurement off of assumption 1, and that is that the change of the enzyme substrate over the change of time equals 0. Because it's constant, there is no change. So we have the equation, the change of enzyme substrate complex over the change of time is 0. There is no change. Now the other thing we want to look at is the total amount of enzyme. So the total amount of enzyme available in a solution is equal to so we're going to say the concentration, is equal to the concentration of enzyme by itself plus the concentration of the enzyme substrate complex. Now recall from our video on the lesson on reaction rates that the velocity of a reaction, let's say it's a bimolecular reaction, because enzyme and substrate complex we have two things that are separate, and then those two things come together and they form one thing. That is a bimolecular reaction. And so for a bimolecular reaction, so we have A plus B yields C, or the velocity for that, if these are elementary reactions, meaning there are no intermediate states, then the velocity would be the concentration of A times the concentration of B times the rate constant. So the velocity of the formation of the enzyme substrate complex, so we have E plus S yields ES, so the velocity of that would be equal to K, K1 times E times S. But we know from equation number 2 that we can express the concentration of the enzyme a little bit differently. We can say that the concentration of the enzyme is equal to the total enzyme minus the enzyme substrate complex. And so we can rewrite this equation, and in here we're going to replace the concentration of the enzyme. So the velocity of formation is equal to K1 times the concentration of the total enzyme minus the concentration of the enzyme substrate complex times the concentration of substrate. And then we know that the disappearance, the velocity that the enzyme substrate complex disappears, velocity of disappearance, is equal to K minus 1 times the enzyme substrate complex plus, it can disappear two different ways, so plus K2 times the enzyme substrate complex. And let me make that look more like a 2. Now's the time where we go back and we remember our assumption. Our assumption was that the change of ES over the change of time equals 0. So that the enzyme substrate complex, the amount of it doesn't change. That means the velocity at which it forms has to equal the velocity at which it disappears. Since the formation velocity and the disappearance velocity are equal, we can combine these equations. So we would get K1 times the concentration of the total enzyme minus the enzyme substrate complex times S is equal to K minus 1 times the enzyme substrate complex plus K2 times the enzyme substrate complex. Now before I move on any further, I want to note that we can actually rewrite this as the velocity of disappearance is equal to K minus 1 plus K2 times the enzyme substrate complex. And so all I did really was I factored out the enzyme substrate complex from this equation. So the next thing I'm going to do is I'm going to divide this equation by K1 to bring it over here. I'm going to divide over here by enzyme substrate to bring it over here, and we get another equation that is total enzyme minus enzyme substrate complex times the substrate divided by enzyme substrate complex is equal to K minus 1 plus K2 over K1. Now let me point out really quick that we have moles minus moles. So our unit for this whole thing will be moles times moles. So we got moles times moles, that's moles squared. Then we divide by moles, so we end up with our units for this. The units for this whole side of the equation would be in moles. Or rather, molar, so it's a concentration, it's not an amount. Now secondly, notice that K minus 1, so the enzyme substrate complex, whether it forms a product or whether it forms the substrate and the enzyme, this is a unimolecular reaction, and so it's first order. So the units for K minus 1 are seconds to the negative 1, and the units for K2 are seconds to the negative 1. And then for K1, so going this way, it's bimolecular, so the units for that are moles to the negative 1 times seconds to the negative 1. And so what we end up getting is when we add per second to per second, and then we end up with our total top value is seconds to the negative 1, and our bottom value is in molar times seconds to the negative 1, and so this is negative 1 as well. So these cancel out, and we end up with a unit of 1 over moles to the negative 1, which is equal to molar. So we have the same units on both sides of the equation. And all this tells us is that, yeah, we did our math right. Now the second thing I want to talk about is this. This right here is an important part of Michaelis-Menton enzyme kinetics. So K to the minus 1, so basically enzyme substrate breaking apart plus enzyme substrate forming divided by enzyme substrate breaking apart plus enzyme substrate forming product divided by the formation of the enzyme substrate complex. This whole ratio has a special meaning in Michaelis-Menton kinetics. So notice first of all that these are all constants. This is a rate constant, this is a rate constant, this is a rate constant. And so the ratio of all of these constants gives us another constant called the Michaelis constant. So Km, or capital Km, is called the Michaelis constant. And remember that the Michaelis constant has units of molar. Now also remember that K minus 1 plus K2 over K1 was equal to something else. So it was equal to the total enzyme concentration minus the enzyme substrate complex times the substrate divided by the enzyme substrate complex. So we just want to take this in terms of Km, and we're going to replace Km with this. We're going to rearrange this equation. And so what we would actually do is I'm not going to write all this out, but we'd multiply by ES, and we get ES times Km. Then we would distribute the substrate, so we get ET times substrate minus ES times substrate. Then we would add the ES times S to this side, and then at that point we would have ES times Km plus ES times S. We would factor out the ES and then divide by Km plus S, and we would get that ES enzyme substrate complex is equal to ET ET times S over Km plus S. Now here's the most important part of all of this math. We want to find the velocity that we make products. That's really what we're interested in. How fast are we going to make products when we add an enzyme? And so the velocity of product formation is equal to it's equal to the change of product, right? The change of product over the change of time, which is equal to negative change of enzyme substrate complex over the change of time, which is equal to K2 times the enzyme substrate complex. So now what we want to do is we want to replace enzyme substrate complex. We're going to substitute because this is equal to this, so we're going to substitute this in right here. So we're going to say that the velocity is equal to K2 times the total enzyme concentration times S times the substrate concentration divided by the Michaelis constant plus the substrate concentration. Now here's the pivotal point where we finally get the Michaelis-Menton equation. So K2 times ET has a special meaning. So if we have so much substrate, if we add so much substrate initially that we completely saturate our enzyme, at that point we would say that the total enzyme is equal to the enzyme substrate complex. So is equal to the enzyme substrate complex. So ES would equal ET, but it would only equal ET at whenever it's saturated, which would make the maximum velocity. So that would be at Vmax. So if we look at this equation right here, we would know that Vmax is equal to K2 times ET. So we can substitute K2 times ET in this equation for Vmax. So the velocity is equal to Vmax times S over Km plus S. And just so I can make sure I'm being very clear and not confusing, we said that the velocity of product formation is equal to K2 times the enzyme substrate complex. But we also know that whenever we are at maximum speed, it's because all of our enzyme is saturated with substrate. So ET equals ES whenever we're at our maximum velocity. So V would be Vmax at that point, and K2 times ES would be the same thing as K2 times ET. So this is the Michaelis-Menton equation. It's the equation that we worked on. It's the equation that we want. This is the most important equation in the whole thing. But there's one more thing we want to do to manipulate this to find one more property of enzyme kinetics. So the first thing I'm going to do is invert the entire equation. So I could, if V equals Vmax times S over Km plus S, we can say that 1 over V is equal to Km, capital Km, plus S over Vmax times S. And then the next thing we're going to do is multiply both sides by Vmax times S. So we get Vmax over V times S is equal to Km plus S. And then we subtract this S to the other side. So you get Vmax over V times S minus S equals Km. And you can actually even simplify this even further by factoring out the S. So you would get Km is equal to S times Vmax over V minus 1. Now we're going to do something kind of fun. We want to set Km equal to S, and we can do that by making this term equal 1. So what would make this term equal 1? Well, Vmax minus Vmax over V has to equal 2, because 2 minus 1 equals 1. So whenever V equals half of Vmax, so whenever V equals 1/2 of Vmax, this whole term will equal 1. And so 1 times any number is that number. So for example, if Vmax was 10 and V was 5, 10 over 5 equals 2, 2 minus 1 equals 1. So we can say when V equals 1/2 of Vmax, at that point Km equals S. And so you can actually use a Michaelis-Menton plot of the concentration versus the concentration of the substrate versus the reaction rate, or the velocity, and you can determine what Vmax is, and then you can find 1/2 of Vmax and determine what the substrate concentration is at 1/2 of Vmax, and you'll know what your Km value is.